Recurrent neural networks, RNN architecture, and backpropagation. Through time. Greetings, learners. Today, we're going to explore the appealing world of recurrent neural networks, RNNs. By the end of this lecture, you'll grasp the principles of RNN architecture, its potential pitfalls, as well as the concept of backpropagation through time, BPTT. Let's get started. RNNs are unique because they can process inputs of any length, thanks to the maintenance of a hidden state that represents historical information. In essence, RNNs can map from input sequences to output sequences, range secu. In an RNN, the recurrent layer passes its output back into itself. Each recurrent neuron has two sets of weights, one for the inputs and one for the outputs of the previous time step. This structure effectively allows the network to remember information from one step to the next. The training of RNNs is not without its hurdles. During training, RNNs can suffer from exploding or vanishing gradients. Furthermore, learning long-term dependencies with RNNs is difficult owing to the vanishing and exploding gradients problem. One technique for teaching RNNs is backpropagation through time, BPTT. BPTT unfolds the entire input sequence into a computational graph to compute the gradient of the cost function. However, BPTT is computationally expensive and can suffer from memory limitations. To address the vanishing gradients problem, variations of the basic RNN, like long short-term memory, LSTM, and gated recurrent units, GRU, were introduced. LSTMs use a memory cell to store information for either long or short periods of time, while GRUs use a simplified gating mechanism. RNNs can also be bidirectional, allowing them to draw on future context. In a bidirectional RNN, the output of the neurons depends on both the previous and future inputs. Deeper RNN models, known as deep recurrent networks, stack multiple recurrent hidden layers on top of each other, which makes them more powerful than shallow RNNs, though they can be harder to train due to the increased depth. Echo state networks and reservoir computing are architectures that only train the output weights. These techniques help to simplify and speed up the training process. RNNs are ideal for sequence prediction tasks, time series analysis, and natural language processing. Their ability to generate sequence elements one step at a time also makes them useful for text generation. Despite their strengths, RNNs can suffer from model instability, where small changes in the input can lead to large and unpredictable changes in the output. Additionally, they often require extensive hyperparameter tuning and careful initialization to perform well. Modern architectures, such as the transformer model, have started to replace RNNs in certain tasks due to their constant path length between any two positions in the input. Nonetheless, RNNs still hold a significant place in the realm of sequential data processing. In conclusion, recurrent neural networks provide a powerful method for dealing with sequence data, despite particular challenges in their training processes. The innovative techniques and architectures developed to enhance RNNs demonstrate the continuous advancement and potential of this exciting subfield of machine learning. In our next session, we'll continue our journey into the realm of deep learning and explore the world of convolutional neural networks, especially their applications in image and video processing. Stay curious and keep learning.